Hey Ramblers, this video deals with Chapter 8.5, which covers three theorems which are a direct result of the similarity of triangles. The first theorem is called the side splitter, and it helps us whenever a line parallel to a side of a triangle intersects the other two sides. The theorem after that, I believe it's theorem number 66, is a direct result of the side splitter. But we can extend the side splitter to more than just two parallel lines, and we'll see that when we have three or more intersecting two transversals, we have some proportions there as well. Finally, the last theorem is called the angle bisector theorem, and it's a favorite of the ACT and other standardized tests. The results are pretty simple, but the means by which they got there isn't. And so I really think it's good to walk through the proof and see where the results came from. Either way, you do not have to memorize the proofs that I'm showing you, but simply be familiar with their results and how to apply them. Okay, I hope this video helps you to do that. Take good notes and good luck. Okay, let's take a look at these three theorems that involve the proportions, and we'll start with the side splitter theorem. Okay, well, this is a very common expression or a common diagram expressing side splitter. And it involves a parallel line, ED, crossing two sides of a triangle. ED is parallel to the third side, BC. And it can cross anywhere. Here it looks like it's almost in the middle, like a midline. But the theorem is true if ED crosses the two sides of the triangle very close to that vertex or very far away. It really doesn't matter. It's going to hold true that AE, which I've called X, over EB, which I've called A, equals AD, what I've called Y, over DC, what I've called B. All right, let's walk through the proof just to see where this comes from. All right, from the givens, we can derive that, we can conclude that we have two pairs of corresponding angles. The angle here at E is going to be congruent to the angle down there at B, and the angle on the other side at D is going to be congruent to the angle over here at C. All right, now because of those two pairs of congruent angles, we know that triangle AED, the triangle on top, is congruent to the large triangle ABC by angle-angle. All right, as a result of that, I can set up the proportion that AE, this part of the side, over the whole side AB is congruent to AD over the whole side AC. By the means extremes product theorem, I can get this product of two factors, AE times AC equals AD times AB. Now, just for my own sanity, I'm going to substitute X in for AE, Y in for AD, A in for EB, and B in for DC. And when I do so, you can see that I express AC as Y plus B. Take a look at the diagram to confirm that. And I can express AB as X plus A. Once again, look to the diagram to make sure that makes sense to you. When I distribute the X on the left side and the Y on the right side, I get two pairs of terms on each side of the equals, and one of the terms is an XY on both sides. So I'm going to subtract that from both sides, and I'm left with BX equals AY. By the means extremes ratio theorem, I can see that X over A equals Y over B. If I substitute back into my original expressions for those segments, I get the desired AE over EB equals AD over DC. All right, that leaves us with just this theorem. If a line is parallel to one side of a triangle, just as ED is to BC, and it intersects the other two sides, then it divides those two sides proportionally. And that's called the side splitter theorem. It helps you to solve for either A, X, Y, or B. Okay, let's take a look at theorem 66. Okay, let's take a look at Theorem 66. It's really closely related to the side splitter theorem. In fact, it's just an extension of it. So here we're given that FG is parallel to HK, and that's parallel to IJ. So rather than just having two parallel lines, we have three parallel lines. And we want to prove that IH, this segment here, the segment on top, to the segment on the bottom, HF, is equal to JK, the segment on top, to the segment on the bottom, KG. All right, again, let's take a look at where this, how we prove it, not to memorize it, but just so we can understand the theorem better. Okay, I'll start out with, let's scroll up a bit, and we'll see that we get through the givens. The first step is going to draw IG. That's a segment from I to G, and it intersects HK at N. Well, when it does that, it creates two triangles. Now, those two triangles, we can apply the side splitter theorem to each one. So in step 3, you can see that IH, the segment on top, is to HF, just as IN is to NG. In the orange triangle, if you kind of think of it as being an upside down example of the side splitter we just looked at, you'll see that IN to NG equals JK to KG. That's just the side splitter theorem again. So you'll notice maybe that both of these have this ratio. Both of these proportions have this ratio in them. So I can set IH over HF equal to JK over KG by the transitive property. And that is exactly what they want us to prove. That IH, we can call that X if you like, call HFA equals JK over KG. So it's really just like the side splitter theorem. Please get this one in your notes. Again, not so much to memorize it, but so that you can apply it to problems that come up in the exercises. So the final theorem is going to be this. If three or more parallel lines are intersected by two transversals, then the parallel lines divide the transversals proportionally. So I could even add more parallel lines here, and all the parts would be proportional. Okay, let's take a look at Theorem 66. Let's take a look at the angle bisector theorem before wrapping up. The angle bisector theorem is a favorite of the ACT and other standardized multiple choice tests. So it's important that we not only learn it for this chapter, but we become familiar with it enough that you'll be able to bring that with you for later use in your high school career. It typically works like this. We have a triangle, POQ, and one of the three angles, in this case it's angle POQ, is bisected by a ray. I've only drawn segment OR because that's all we need for our proof. So angle POR is congruent to QOR. Can we prove that segment PR to RQ equals OP to OQ? In other words, are the portions of the third side, can we prove that they're proportional to the other two sides? Well, let's take a look at the proof. All right, if we start off with the givens, we'll notice that since OR bisects the angle at POQ, angle 1 is congruent to angle 2. Well, then we're going to add a couple of auxiliary lines. The first is going to be a parallel segment to this bisector. So OR is going to be parallel to this new segment. And then we're going to extend segment OQ until it meets this parallel line at point M. Now, you may recognize that in triangle QMP, we have a segment drawn parallel to the third side. That's all we need to establish the side splitter. So in step 6, we can conclude that PR is over RQ is equal to MO over OQ by the side splitter theorem. All right, let's take a look at angle 3 and angle 4. Since these lines are parallel, MP and OR, OP is a transversal. So therefore, by alternate interior angles, angle 1 is congruent to angle 3. But we also know that angle 2 is congruent to angle 4 because those angles are corresponding angles. We know that angle 3 then must be congruent to angle 4 because of the transitive property from steps 3, 7, and 8. So, therefore, OP must be congruent to OM because if angles are congruent, then sides congruent. That allows us to make a substitution into our step number 6, that PR over RQ equals OP over OQ, which is exactly what we needed to prove. Okay, so it's true. Let's get it down then. The angle bisector theorem says if a ray bisects an angle of a triangle, any angle of a triangle, then it divides the opposite segments in the opposite side into segments that are proportional to the sides.